Welcome to the first part in the series of lectures on water pH and buffers. So your skills to master here, number 1, you're going to explain the chemical basis of the polar nature of water. Why is it polar? Tell me. Define pH based on the concentration of protons in solution and how pH is related to pOH. You're going to describe the chemical and functional properties of buffers, what makes them buffers, how do you make a buffer, and you're going to justify the use of buffers in biochemical reactions. Okay, so first off, I've started off by drawing the chemical structure of water. You should absolutely have this down without even thinking about it. H2O, chemical formula, chemical structure. And as we know from the periodic table of the elements, that the elements to the right and up are actually this idea called electronegative. Of course, when we do this, we ignore the noble gases all the way on the right-hand side. Because they're noble, they don't react with anything. So this makes the most electronegative atom fluorine. Immediately next to that is oxygen. Okay, so that makes oxygen a very electronegative atom. Electronegative. And so what that means is that the oxygen, when it forms covalent bonds, is going to pull the electrons towards itself. Electrons have a negative charge, so when these bonds are formed, it causes a slightly negative charge to the oxygen, which is pulling those negative electrons towards itself. And because we formed a slightly negative charge here, we have a slightly positive charge on the opposite end. Overall, this creates a dipole moment. It's having a moment. And because these bond angles aren't immediately straight across, overall, this molecule has a positive end and a negative end. And that is what makes it polar. Just like the poles of a magnet have a north pole and a south pole, polar molecules have an uneven distribution of charge. Okay, so that's what makes it polar. Because of this electronegative element and because of these because the bond angles are not perfectly straight across. If they were perfectly straight across and you had dipole moments that looked like this, they would cancel out. So bond angles, electronegative atoms creates a dipole moment. Okay, so water is really wonderful and it's absolutely fascinating to study, and 80% of cells are made of water, 80% of you is made of water, 80% of the earth is made of water. It's one of the most abundant elements on the planet, or one of the most abundant molecules on the planet. Goodness, elements. Whew. Long day for me. Okay, and as you may remember from general chemistry, water in solution exists in several forms, H plus and OH minus. And these exist in equilibrium. So the majority of the time, water molecules are together as H2O, but some percentage of them exist as H plus and some percentage of them exist as OH minus. So anytime you're in a water, remember that H plus is around and OH minus is around, and you've seen this already in organic chemistry. Okay, so what does this mean for us? Well, the presence of H plus in solution tells us a lot about the solution by this idea of pH, because the pH is the opposite log of the concentration of H plus. So the more protons we have in solution, the lower the pH is, because it'll make this number bigger and more negative, right? So more H plus will drop the pH and make solutions acidic. Similarly, if we have more OH minus, it's going to increase the pH and make it more basic. Okay, and remember from general chemistry that pH plus pOH equals this magic number 14, and we get this 14 based on the pH scale, which, just quickly to remind you, goes from 1 to 14. You can't have 0. That would be impossible. And right around 7 is the neutral range. Anything less than that is acidic. Anything more than that is basic. The only compound that we know of to be exactly pH 7 is pure water, which pretty much only exists in a lab. You don't really find that without ions in it or without anything dissolved in it in nature. So we actually live very, very close to this pH 7 range. If we deviate too far from this, terrible things happen to our bodies, because at both ends of this, our proteins will start to denature. And we'll talk more about the specifics of that in a few chapters. So in order to maintain the pH at what we want when we're studying these proteins in solution, we've taken them out of their natural habitat. So how do we make sure that the proteins stay folded? We keep the pH constant with combinations of chemicals called buffers, which resist the change in pH. Resist change in pH. Okay, so typically these are made from a weak acid and its conjugate base. So these are really, really important in biochemistry because we can maintain the pH and prevent the denaturation of these proteins. And so it allows us to study systems outside of a cell. So we can isolate systems and study them under physiologically relevant conditions. So buffers are going to be extremely important. So another important concept when you're thinking about buffers is that these weak acids and weak bases have to be present in considerable concentration, high enough concentration, in order to prevent changes of pH based on substrates and products of the reaction. High enough concentration, higher than either the substrates or products. Because if the substrates or the products of the reaction are in higher concentration than the buffer, then suddenly these control the pH. So buffers are typically at 1 molar concentrations, whereas substrates and products would be on the millimolar side of concentration.